Hello everyone, December the 2nd, let's do this. Odd, even, linked list. Oh, it's a new one, nice. Okay, given a head of a singly linked list, group all the nodes with odd indices together followed by the nodes with even indices and then return the reordered list. The first node is considered odd and the second so is 1, right? 1. Now that the relative order inside both the even and odd groups should remain as it is, we must have the problem O1 extra space, complexity On. So yeah, you cannot do it just grab the entire list in an array and then do something like that. All right, let's do this. This is good. I always like this type of problem. Linked list, it's fun. You just move things around and see how you can move around. So basically, if you see, I have an odd, an even, an odd, right? So what if we remove these two? Not remove, like swap these to be 1, 3, 2, 4, right? And then if we do this, and this will be even again, so 2, 4 shall stay. And now look at 5. And we'll replace 5 with 5 with what? You don't replace, you insert. Remember, linked list, you can insert. We can insert. So now instead of replace, I just insert this to here, insert this to here. That's it, right? So every time we get an odd, now we get an even, right? And we stay at an even position. The first even position, all the odds going to be inserted right before the first even, right? Right before the first even, and right before the first even. All right, so what is the mechanics? How can we insert right before the first even? So of course we stop at the first even, and we can have, so if the length is 0 or the length is 1, yeah, it's fine. So okay, so we stop at the first even, right? And we do need to know the 1 right before it. So we need a current, not current, like the first even. And then we have the pre, right? The pre. And then when we insert, we'll swap the pre to the inserted one. Yeah, so I think we can do this. All right. Let's see what we got. As always, slow as always, but I got used to it. Oh, I feel like it's getting slower, huh? It's definitely getting slower, the laptop. Day by day. Getting slower and slower. Alright, so this one, we do not do testing. No tests. Okay, so what we say is, if not head, return head, right? If there is head, then we say first even shall equal to head.next, right? So we have first even and the pre equals head. Now what? Now we're just gonna go, let's see, while, so after we do this, we need to have a current, we need to move forward. So we need a first even, a pre is always pointing to first even, and we also need a current. So current will equal to this one as well. Wait, where is current pointing to? Current is going to point into the one after the first even, right? So current, okay, so current equal to first even dot next. So now we set up, And we say while current, right? Say while current. So we have something on the current, which is here. And while current, we're gonna move this to this, and the next current is the current dot next. Dot next, dot next. But what if this is the last one? So it depends, right? So like it's here and dot next. They all end. What if we end at they all end at odd, right? So with an odd, I can always go 2 steps. But if we end at here, then we just done. We move this, and this will go next. Oh, we always have next. We always have next. Yeah. So in this position, I move here. We always have the next and next, which is pointed to none, right? So while current, we're gonna move current to the previous. So the current gonna move to pre. How do we do?
That's fine.
How do we do pre? So we're gonna do pre dot next. Oh, poor kitten. Hey, what happened? Oh no. Got stuck. Alright, poor kitten got stuck. Alright, that actually just need pre. I don't need first even. The pre points to the first even. Right? Wait, hold on. The pre points to first even. So maybe I don't even need. Pre is head. Current is gonna be head. Done next. Yeah, so the current is going to be, hold on. Current is going to be head dot next dot next. But what if we head dot next? We do not have dot next. Well, actually, if not head or not head dot next, we return. Then we guarantee, right? Now we guarantee. So while current is head dot next, right? We say while head, we're gonna insert it in between. So how do we say? We say pre dot next, right? Pre dot next is equal to current, so we insert the current in between, and then current dot next will equal to pre dot next, right? So, okay, no, hold on. We need a temp. Let me give a temp. The temp is actually the first even will equal to pre dot next, and then pre dot next equals current, and pre dot next equals current, and current dot next equals to first even, right? So once we do that, we also need to handle we need another one because we need a 2 at the back and 2 at the front. Because if I insert this one to here, this needs to connect to this. Oh my. So I need a okay. So this is going to be pre first even. Right? That's pre first even. And then we may have another pre. So that one is pre first even. That one will be pre current. Right? That will be pre current. So okay, let me think again. So pre first even is this one. And pre current is here, right? So pre current is this one. So it's a head. That's actually head dot next. All right, and this is the precurrent, and we say while precurrent dot next. Okay, while precurrent dot next. So precurrent dot next. While precurrent dot next. So I need to move this to here, right? Can I just go slower so I don't have to go back and forth? All right. So while precurrent dot next, I say first even, right? First even is equal to pre first even dot next. Okay, now we grab the first even and then pre first even dot next will equal to precurrent dot next. Right, so we move this one here, and once we're done, we say precurrent dot next equals first even. Right, so now we move them around. Now once we've done that, so the precurrent dot next has been reconnected here. So now what we need to do is to do precurrent dot next need to equal. Oh shoot! I need another thing. So in the current equals precurrent dot next, right? And then pre equals that equals current. No, what we want, no, hold on. What we want is next. Next is equal to precurrent dot next, right? That's the next thing. So these two getting out, and then we say pre first even dot next equals precurrent dot next. Yes, we move there, right? And then precurrent dot next, which is this, but now we point into FE, and finally precurrent dot next. So precurrent dot next need to pointing to next, right? So we're pointing to this one, and then once we all done, so everybody is done. Now we need to reassign pre first even. So pre first even, because I push something in here, so pre first even need to equals pre first even dot next. All right, so pre first even move one step forward. How about the precurrent? Well, precurrent shall equal to precurrent. So precurrent is still here, and if we say precurrent dot next, we go to this. Yes, that's actually true. We just need to do precurrent dot next. So we went here. So now the precurrent is here, and the first even is this one. And then from here I can go again. Precurrent dot next is this is true. So this will go between these, and then this will go forward. Okay. When do we break out? Well, that's the precurrent, right? So if that's the end, right? So precurrent. Oh, precurrent dot next. This NE will be a none. So precurrent dot next is equal to none, and precurrent will go to that. Yeah, and we break out. Okay. So what if we end at this? Okay, we end at this. Then precurrent dot next is none already, so we end. Oh, that's fine. So we can just return head. Can we like simplify this? Oh my god, this looks just ugly. Pre next equals precurrent dot next. precurrent on next equals this precurrent next reassign. I guess that's fine. All right, let's try this. Press the wrong button. Let's try all of them. So that's one. I can use a test case and oh, that's fine because the edge case already considered. That's the edge case. All right, so just run this. Let's see how it goes. None type has no. Oh, hold on. Precurrent equals precurrent on next. So basically, I just need to say while precurrent and precurrent on next. That was my guess. Okay. Try it again. Yep. This time I think it's right. Let's go for it. There we go. Got it. So basically here we say while precurrent and precurrent on next. So this is well, it's not hard, right? It's just you need to get your mind straight. I don't know how number 328, I think. So it's this is not hard in terms of algo, but the logic does require some thought, right? The logic does require some attention. The idea is to keep a pointer, right before the first even node, and keep another pointer right before the next odd node. Then we simply insert the next odd node before the first even node. So O(n) and O(1) time, O(1) space with how much time? 44 milliseconds, or that's actually only 68. All right, let's see if there are any better solutions. We have solution. So solution, step 0, even head. Head odd final. Oh, I think what they do is, they create a new even head. Oh, okay. So I'm doing it along the way. They just create an even head. Every time you got an even, just put it out. You got an even, is put it out. And when it's done, then we're done. Now we just replace. Nice, good. Yeah, it's pretty standard. Want to try this? Yeah, let's try this. Could be interesting. I mean, logic-wise, I think it's easier actually than thinking this way. So this is from the official solution. It has simpler logic than solution 1. We create another linked list for all the even nodes. We extract all even nodes into a separate link the odd nodes to the even nodes at the end. Yep. Okay, but the star will be the same. I just oh, it's fine. I'll just do this. So we can say odd head or even head, right? Even head equals head dot next dot next. All right. That's the even head. Head. No, it's hard not just head dot next. That's the even head, right? We have head dot next. That's the even head, and odd current equal to odd current is equal to head. I need to remove this, right? So odd head is actually not odd head, it's odd pre, right? It's odd pre equals head on next, which is the same as even head. And I have even pre equals to even head. Okay, so when I keep moving forward, so we have odd pre, right? So let me think. So we have this is even head, and even head shall be a dummy. Even head shall be a dummy, which is just node. Just list node. Right, that's a dummy. Even head is a dummy. And we have odd pre. So it's the node before the next odd. Right? So odd pre is head on next. And even pre is nothing at this point. Right? So then what we do? The even node. Well, the odd pre is at the even node. No. Odd pre is head. Odd pre is head. So we're going to push this one to here. Right? And it's even head and even tail. Right? So even tail will equal to even head. That's when we start, right? And then we say while odd pre, right? While odd and odd dot next, right? So we have odd dot next. So odd dot next is the even node. So we're going to put odd dot next push into the even, right? How do we do? And we simply say even tail dot next will equal to odd dot next, right? And then odd dot next needs to equal to odd dot next, right? Odd dot next. Hold on. So odd dot next. So this one pointing here So r.next. So r.next is this. So r.next equals to r.next.next. So that's removing this. And last one, even tail equals even tail.next. So r.next equals to r.next. So this linked, right? And then even come out. So we say odd equals odd.next. So we're going here. It's pointing. So the even tail is actually pointing. This doesn't matter. And then we're going to check for odd, and check for odd.next. If we have, we just keep going. So eventually, if we end at an odd node, right? So we remove this odd.next equals the odd node, and then odd dot next is nothing. So we break out, right? We break out, and when we break out, right? When we break out or odd, what if it's an even node? We add an even node. So an even node will say r.next equals r.next. So r will become a none. So we all break out, right? So odd will be pointing to, ooh, I have an issue, because if we end at an odd node, then if we do odd equals odd.next, that's going to be a problem, because odd becomes none. We need to keep it at the last odd node, right? We need to keep it at the last odd node, which means r.next equals this, and we say if, right? If r.next, then we move. Otherwise, we do not move, and we check for this. So this is making sure odd always points to the last node, actual node of the odd. So now we break out, first thing, even tail, right? Even tail always equals even tail dot next. So even tail dot next needs to be none. So we turn it off. And then odd dot next need to equal to even head dot next, right? And we're going to return head. Yep, I think this one shall work. Give it a shot. So slightly different, but I think logic-wise, it is easier to handle. Right, it's easier to handle. And then we have like a pre something, and a pre first even, a pre current. Yeah, that's a little difficult to handle. This one is easier to handle, to understand, basically. So I'm gonna run the code. This is correct. Well, it's a little slightly faster. Slightly faster. So this one we hit 40 milliseconds and a 86. I think. Alright, so that's that for this. Good. Not too shabby. Alright, let's go for another one, which is gonna take a long time to load. Oh my god. It's 11:49 right now, so I think it will take at least 5 minutes to load based on the performance. Yeah, I think 5 minutes is a good estimate. It's ridiculous, right? I know. Look at this. It can't even load. No, that's 1 minute. So wait for 1 minute. I just click difficulty. Okay. Oh, maybe it'll be shorter than 5 minutes. Okay. Page 4. All right. So we did additive number yesterday. All right, let's try the super ugly number. Super ugly number. Well, super ugly number is super ugly. $52. So we waited for 3 minutes already. Right? We waited for 3 minutes. It's 52. Maybe it will take 5 minutes just to load. Oh, here we go. There we go. Come on, come on. There we go. Super ugly number is a positive integer whose prime factors are in the array primes. Given an integer n and an array of integers primes, return the nth super ugly number. The nth super ugly number is guaranteed to fit in a 32-bit 6-signed integer. Wait, hold on. A super ugly number is a positive integer whose prime factors are in the. So, okay, so the 12th super ugly number. So we just do combine. Wait, hold on. I understand. Given integer n and an array of integers prime, return the nth super ugly number. These is a sequence of the first 12 super ugly numbers. Why is 1 there? Whose prime factors? Oh, wait, hold on. Oh, 1 has no prime factor, therefore all of its prime factors are in the array. Huh? Oh, the empty set, right? 1 has no prime factors, so 1's prime factor set is an empty set. An empty set always belongs to this prime set. That's why 1 is always there. 2 is in there, 3 is not, 4 is in there, 5 is not, 6 is not because 6 contains 2 and 3. 3 not there. 7, 8, 13, 16, 15, 19, no 20, no 21, it's no 3, 22, no 3, no 4, no 6, 25, no 26, 28, 32, okay. N is 10 to the 4th. Interesting. Can we see this? Can we see this? So what do you think? Oh, hold on. N is to 10 to the 6th. Oh, we probably cannot see 10 to the 6th. Holy guacamole, 10 to the 6th. That's a giant number. We cannot get a array 10 to the 6th. I just basically, I'm saying this, it's not possible to do 1 by 1. 1 by 1, 10 to the 6th, what's that? That's 1 million. Right? 1 million. And then that's just n. N doesn't go, it's the nth. So the actual value can be much larger than this. So basically, what we want is a combination of the prime length. The prime length is 100, right? So all the combination of prime length will go to, is that 2 to the n? That's a huge value as well. Is it 2 to the 100? That's a large value. But all we need to go to is the 10 to the 6th, right? So, no, I don't think you can do it this way. Well. So 1 is always in there. That's right. That's just a given. So with a start, when I say 2, is 2 in there? 2 is not in there. Right? 2 is not in there. 3. Oh wait, hold on. Let's focus on this. So 1 is in there. 2 is in there. 3 is not in there, so 3 we go separate. 4, how do we know 4 is in there? Well, because 2 is in there, right? Do we have to factor this thing? Okay, 4 is in there because 4 divided by 2 is in the set. So 4 is in there. And then 5 is not in there. Because 5 divided by we have to divide every single one. Five divided by, we have 100 prime, so I think it's okay if I go 5 divided by every single one, and say it's not in there. Okay, so 5 is not in there. 6 I divide by the prime numbers, and once I divide, if I find it in the rejected list, then it's not in there. 6 is not in there, in the rejected list. 7, we'll do again, divide, it's in there, so 7 is good. 8, divide by 2, it's in there. 9, nothing can be divided, nothing can divide 9, so 9 goes down. 10 we divide as 5 is in the other set, so 10 goes down. 11 is not in it, right? 11 is not in it. Okay, 11 is not in it, so 11 goes down. 12, 6 is in the bottom, so 12, no. So we do have to go one by one. Man, 1 by 1. You gotta be kidding me. This is gonna time out. Even if we keep like a 2 set, right? We have 2 set, but it's gonna time out for sure, right? For sure, it's gonna time out. But depending on how lenient this is. So basically, my current idea is we're gonna go through number one by one, right? For each number, we gonna do divide for all the primes, and if none of them can divide, then booyah, that's it. Right? None of them can divide, then booyah. And so if someone can divide, then we can look into the set that we have. So we're gonna have a viable set and a rejection set, right? Oh, we just need a viable set. We don't need a rejection set. We just need a viable set. So in the viable, if it's in the viable set, then we're good. If it's not in the viable set, then we're bad. So the total runtime will be on times 100. Jesus. We'll give this a shot. I mean, we need to give it a shot because I think the other day I had a solution, but I was just afraid that it's going to time out. But in the end, it did not. Right? The idea did not time out. This one, we're going to do the same. Just give it a shot. Right? Just give it a shot. It might work. But memory-wise, oof, I'm not sure. The nth ugly number. I'm pretty sure maybe this question will have a math solution, so we don't have to check one by one. I don't know. So what we need is a set, right? Is a set. We're gonna call it rest set, viable set. Viables equals a set. It will have one in it. No matter what, one will be in it. And we just say while len. Oh, we want, what do we want? We want the actual value. Huh. Actual, alright, I just say if n equal to 1, return 1. Alright, and then we have this, and we say while len variables, that's O1, right? While len variables is smaller than n, right? Then we say res that is smaller than n. What we do? Oh, we need to have I. Let's start with 2, right? Let's start with 2. So I'll len this is smaller than n. Then we say I. I will try to say if, to see if I can be added to it, right? So we say check. I'm gonna check I. So for p in primes, we also have a limit, so we don't have to check. But that's only 100. Right, that's fine. P in prime. If p squared, right? P times p. If p squared is larger, oh, might as well sort it just in case. So primes, I'll sort, right? So if p squared is larger than I, then break, right? That means it doesn't belong. Then we just we break. Otherwise, for each p, we're gonna say if I mod p, if that one equals to 0, we can actually use div mod. Actually, wait, why do you need div mod? Yeah, we do need div mod, so I need a quotient. right? So in the quotient of remnants equals div mod, right? I divided by p, right? So we say if r is equal to 0, so it can be divided. Then we say if q is in variables, then variables dot add I. Right, the variables dot add I, and move on. Right, and then we move on. Then we break as well. Else we check until we cannot check anymore. So this has to be like this, and q, then variables dot add. Once we add it, we can break it, and then go back. Before we break it, I needs to. Oh yeah, once we break it, we can just go I plus equal 1, right? I plus equal 1. Okay, so here, if len variable is smaller than this, and then we do this, all right? We add it, and I plus equal to 1, and then come out. They will equal to, it's already equal to n, and then we'll break out. So we just need to return, because I already add 1, so return I minus 1. Right, if it's this, then we just keep going. If it's this, it's divisible, we check, right? So I'm going to try. So first one, we have this. Answer should be 32. Second one is 2. Oh, this one is no need because that one just 1. What's the first one? 12. And this one 1. It definitely works because I checked this as a special case. This is an n, super ugly number, n and primes. Prim is not defined. Of course it's not defined because there's no prim, then a prime. I was typing too fast. Oh, there's also no primes. Primes. Oh, hold on. Cancel. We have an issue. This one's fine. For this, for p in primes, div mod, unless I got div mod wrong, but even if I got div mod wrong, but there's no variable. Hold on, let me see. Print I, P, Q, and R. Alright, hold on, I think I got it wrong. So I is 4, P is 2, quotient is 2, R is 0, right? And R is equal to 0, yes. Q is not in variables? What the heck? How is Q not in variables? In the first one, I have 1 in variables already, right? And I is 2. So is 1 smaller than, so for P, first prime should be 2. I say 2 times 2. Ooh. That is a problem. Yeah, it works for if I can be factored. That means I don't go for the prime that's larger than me because it's not going to work. But This one also means if I is a prime, then you want, okay, let's just not do this. Let's just not do this. Yep. We'll go to all the way to 32. Okay. So check whether I is viable. And the first one makes it viable, then we're gonna break it. And the second one definitely will pass. Okay. Ooh, very nervous. Not sure. And we can run a few more test cases if we want. For example, we can simply, make, let's create a bigger one, right? Let's do like 10,000. 10,000 requires a lot of prime numbers. 10,000, that's log 10,000 divided by log 2. I need 13. So 2, 3, 5. I'll just put them in. 7, 11. That's a 1, 2, 3, 4, 5, 6, 7. 17. 19, 20, 21, 23, 24, 25, 26, 29, 30, 31. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so let's do probably 1,000. Yep, I mean, it does work, but still, because they only go to 3,000. Okay, let me do this. Prime numbers, right? Prime numbers up to 1,000. I just want to create something big. I want to get 100 prime numbers. Okay, let's get 100 prime numbers. So I have 25. Right, so I have 25. Hold on. Let's do it better here. So 25 to start. Yeah, I'm pretty sure we have to remove this. Let's remove that again. Now another 21. This give us what? This give us 46. Right? This gives 46. And this give us 62. No, I think that's 62. So I have 62 values. 2 to the 62. Oh yeah, that's way more than enough. That's more than enough. Okay. So I have these values, right? And I think I can call the big gun, the real big gun. 1, 2, 3, 4, 5, 6. All right, let's see. Ooh, look at that. Yep. Yeah, it's in timeout. Let's try. Regardless, let's try. If it times out, then we try to figure a different thing. I try to figure something else out. Oh, times out. That actually means it's correct. All right, it's correct. We just need to be a little bit smarter. Times out. Exactly. 10,000 will time out. Yeah, 1 by 1 is not good because it's not 10,000. 1 to 1 million. 1 million is too much. Now we passed 81. So this is the correct one, but it's simply too slow. So this one times out. TLE. Now apparently we cannot go 1 by 1. So what would you say? We have to do combinations? But combinations. Binary search. How do you know where it is if you do binary search? Well, I know the largest value. We just multiply all of them together. That's the largest value. That's possible. If we binary search, okay, we search for the center. Then what? I mean, we get a mid value, and from the mid value, I think we can, or can we find the smallest value that's to the left or to the right? Then what? Okay, how do you know its index? Right? How do you know its index that it is in number 12? How do you know the index? I mean, I can do binary search, right? But if I do binary search, but I don't know where in the grand scheme of things, where you're located. What if we just do this, right? So we just go 2, 7, 13, 19, and then grab each one with a times 2, right? So that's the first round, and then everything comes out. We're just gonna multiply again, so that's gonna be 4, right? 26, 38. But then you're gonna miss, right? What you have is not the smallest. No, it's not the smallest. To 10 to a million, but that's not going to be the smallest. Let's come back to binary search. So I have this, right? And then we have a bunch of values between. But I don't know. I don't know. There's no indication on index. First 12. if I can jump, why do you jump 1 at a time? Huh? You jump 2 at a time, 7 at a time, 13 at a time. Okay. Okay, what you saying? So we start with 1. 1 is always in there, right? And we don't have to. We're gonna start with the prime numbers. 2, 7, 13, and 19. Right? And then for every 1, 2, which is gonna jump 2. And about we're multiplying. If it is a factor of 7, then we jump by 7. Why though? Analysis. So I have 2, right? So all even numbers. All even numbers are part of it. So we can find the 12th even number. The 12th even number. Yes, the 12th even number because the actual value must be smaller than the 12th even number. It's easy to understand because we have other numbers that can jam inside, right? So the maximum we can get is going to be small. So the 12th, this is the 12th even number starting from 2. Well, isn't that 4? Oh no, that's actually not right because small cannot be inside because they don't have a factor. First, 2, 4, 6. But you need to say 6 is no good, right? Oh. That's simple. Let's just say I have only one value. Let's say prime number is just 2, right? If prime number is just 2, then everything must be a factor of 2. So we basically say we're going to start from 2, and then 4, 8, 16, blah, blah, blah. So if we have n, so it will be just 2 to n. Well, it's actually 2 to n plus 1 because I have 1, right? So that's one value. It's 1. Now I add another one. Say you have 2 and 3. I have 2 values. Now we have 2 values, things are just a little bit complicated because we can have 2 to the power times 3 to the power, right? So we can say 2 to the, we can say 3 to the 0 power, and then 2 to the 0 and 1, 2, 3, 4, 5, and then 2 to the first power, and then 3 to the 0 power. Yeah, that's from 0 to the end, and then 3 to the 1 power, and then 2 to the 0 to the end, right? Can we guarantee the size? Well, let's say 0 is 1, so that's just 2. Times 1, 2, 4, 8, 16, blah, blah, blah. And now that's 3 to the 0 power. 0 to the 1 power, what we're going to have is 3, right? And then, because 1 times 3, and then 2 times 3, right? 4 times 3, all the way. So all of these are bigger than its corresponding, right? All of these are, of course, bigger than the corresponding 2 to all these powers, right? They're all bigger. Therefore, if we want to find, let's say 2 and 3, right? Let's say 2 and 3. I should do it here. It's fine. 2 and 3. Right. If I want to find 2 and 3, let's say find the 50th value for 2 and 3. Right. 50th value of 2 and 3. So what we can do is go 50. So let's say it's 3 to the 0 power. Oh, but hold on. But it could be like 3 to the 2 power, right? 3 to the 2 power. That can still be inside. But hold a second. 50. So like 1 times 3 to the second, 2 times 3 to the second. How do we do this? If I know like a upper bound, I do have upper bound. They said fitting a 32-bit signed integer. So that's the upper bound, right? So I can have the upper bound is just 2 times 31 minus 1, right? That's the upper bound. So if given 2, 3, I can, for 2, I can find all the powers. So I have like 32 values, right? So 32 values I have, so 1, 2, blah, 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 all the way to 2 to the 31st. That's like 32, right? That's 32 values, right? And then I add in the others. 1, 3, 2, 3. So we added them as well. That's what are we saying? What we're saying is we're going to do all the combinations that we can among all the values, right? All 100 values. And do all the combinations. And if any value will break, then we do not in. Wait, how do we do that? How do we do all the combinations? We get 1 out, right? And then, because that's 2, 7. Like I want all the combinations that I can get. So 2 come in. So I have 2. And then 2, 3. And then 2 comes in. So we have 4, 6. 3 comes in. We have 6 and 9. And then 2 comes in again. Wait, I forgot how I do that. So every, hold on. How does this combination work? Like I want all the combinations, right? All possible combinations. So one, that's not all the combinations, because every single one we can duplicate. Otherwise, it's a bitmap, right? It's a bitmap. It's just 100 bits, and then we just go through every single one, right? We'll go through every single one. It's a huge value. But the thing is, we can have. So that is trouble. That is a trouble. So the whole value. Hold on, let me think. So every position we have a value, right? So 2, 3 we have two values. So either a 0. We'll start with a 0, 0, and then we're gonna go 1, 0, 2, 0, 3, 0. Right, this one can go, and then we're gonna set this one to 1, and this one can go until a point where we break. Right. And now, how are you gonna handle this with 100 prime numbers? Well, what if we go large to small? Still, it's so the large value. Like we just go for the limit, right? Basically, the question is how can we find all the combinations that with the value smaller or equal to the limit, and I'll sort them, and then still don't feel right. It still don't feel right. Oh. I is viable. I add to it, right? If I is viable. If I is not viable, and we know all of those are not viable. So like what? We don't go through those? Like 5 is not viable? The non-viables. Hold on, the non-viables. Wait, what are you saying? I scratch out the non-viables. I scratch out the non-viables. How much that's gonna be? We're gonna create a thing with length of 2 to the 31st. So it can be 1, 2, 3. So it can be an array. 1, 2, 3, all the way to 2 to the 31st minus 1. So that's our array, right? And then we have these primes. So we look for the primes that are not in it. And we just scratch out all those numbers. Okay. So like for the first one, we have, and we know the primes all the way to 1000, right? All the way to 1000. So what we want is all the prime that's smaller than 1000. All the prime that's smaller than 1,000. That's a lot. That's a lot of prime smaller than 1000, but I think it's possible. Smaller than 1000. And we just scratch out, right? We just scratch out all the values. Hold on, so primes up to 1000. That's not too much. Right? That's not too much. Primes up to 1000. Okay, that's the list. Prime up to 1000. Right? Okay, so that's the prime list up to 1000. So what we want to do is, when we have this, we're gonna just look for the prime that's not in it, right? And then we just scratch away. So for every one, we're gonna do 1 time of this, 2 times of this, 3 times of this, 4 times of this, and then we're just gonna scratch. Okay? Let's try this idea. Let's try this idea. I mean, it's very unconventional because I'm really, leaning on the restrictions, right? So self n primes right, so all primes will equal to this. That's all the primes. Now we just need to find which are the excluded primes. So excluded will equal to well, I mean, we can do is just that's a set. You can turn this into a set, and it's just a minus, right? Yeah. Hold on, let me think again. So we turn this into a set, and then excluded will equals to all primes minus set primes. So this is the I think that's right. PT Python. So A equals set, let's say 1, 2, 3. B equals set, let's say 2, 3. A minus B shall be 1. Yep. So that's the excluded, right? And we have the limit is 2 to the 31st minus 1. That's a 32-bit signed number. That's the limit. So we're going to say buckets equals to or 0, right? And then if it's actually not, let's say all 1, right? Times limit. Times limit plus 1. Right, times limit plus 1. So that's from 0 to limit. So I have all these. Then what? Then we just sieve, right? Just sieve. How do we sieve? We say for, we go every single one. Because this length is not that long, right? How long is this? Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1, 2, 3, 4, 5, 6, 7, 8. 8 times 16 plus a couple more. So in total, it will not be more than 150, right? So basically, every one is 150. So we should say for p in excluded, right? For every excluded, then we just say, right? We have I will equal to 1, and we say while p times I is smaller or equal to limit, right? If it's smaller or equal to limit, then I'm going to go inside, say buckets p times I is equal to 0, right? And turn into 0. And then I plus equal 1. And then go back, and then we do it again, do it again, do it again. At most, right? Because that's 2 to the 31st. So 2 times 32, 2 times 2, 32 times. So this one will be very fast. I mean, if you think about it, for 3, right? 2 to the 31st minus 1 divided by 3. We only need to go to, well, we need to go to 7. Well, that's actually a lot. If we go plus equal 1. How about, no, this is actually going to take a long time. Because if 3 is not in it, all the 3 needs to be removed. And that's a lot of numbers. That's a lot of numbers. What? Hold on. So what are we saying right now? So what we're saying is, no, I don't think this one works though. Because the limit is too high. Right? The limit is too high. It would take a long time to remove. Hold on. Let me think again. So the maximum value is 2 to the 31 minus 1. That's the maximum value, right? And if any value is in it, then we can compute how many of those values needs to be removed. Let's say 3. Yeah, let's do the example, 2, 3, right? 2, 3, and 50, so 5. That's the next one. So 2 to the 31st minus 1. Right. When you do that, divided by 5. So we have some value that we can remove, right? So we have, but you remove, it doesn't help. How does that help? I remove everything. Yeah, that does not help. No, I don't know. I don't know about this. I mean, might as well. If, I remove everything up until this position for every value. I go I plus equal to 1. That's just... Alright, there's a hint, no hint. Related topic. Hash table, dynamic program, heap. This is ugly number 2. Dynamic programming and a heap. Hash table. How does hash table work in this? This is basically a hash table. I think the idea is heap. How does priority queue helps in this case? A priority queue will pop up the largest or the smallest. Priority queue. I have 2, 7, 13, and 19. Throw that into a heap. And I pop out the smallest value, right? And I multiply the smallest value by the smallest. Okay, now we have 4 comes in. But the smallest value is still 2, right? The smallest value is still, so, whoa, okay, how about every time we add into this pile is the smallest value that is bigger than everybody inside. The biggest value than everybody inside. So we do 2 first, right? Then we find the largest value, that is 2. And we want the smallest value that's bigger than everything. So we times 2. So we push 4 inside, right? Now the biggest value time pop out is 4, right? Then we want to find the smallest value that's larger than 4. So what we can do 2 times 4 is 8. But 7 is smaller than 8. I think that okay. This one seems, so we push 7 in, right? Okay, we push 7 in. Now we're gonna pop 7 out. We don't have to pop 7 out. That's just the thing. 7 is out. So we need to find a way to create based on 2, 7, 13, and 19. We're going to create a value that is the smallest value is larger than 7. How do we do that? Smallest value that's larger than 7. Smallest value that's larger than 7. I mean, I can say 13 is a candidate. Right, 13 is a candidate. But the actual one is 8. How do we get to 8? So it turns into a question. Given a value, can we find the smallest possible value that are factors of all these things? I don't know. How is it possible? Yeah, every time we want to find the smallest value that's larger than everything else that's inside, right? And that value is a factor, can be factored into all these things. How do we handle this? I feel like it's what priority queue is doing, but I don't know. Yeah, given any value, if I can find a fast way to find the next value, well, if we can do that, then they don't need anything. You just keep checking out this value. It's the way of getting this value. All right, no idea. I'm giving up. Let's see. A little bit more hint. I don't want to just to look at the solution. A little bit more hint. Yeah. If I know the current largest is 7, how do I know the next largest is 8? Yeah, like how? Well, how about I go from 7 and I just plus 1, right? And divide it by everything. If it's in it, that's it. If it's not in it, then I plus 2, I plus 3, plus 4. Hold on. This might, so for every value, right, the goal is to find the next value that will be in it. How do we find it? We just add 1, add 2, and then the time complexity is limited to how big the gap is. And as we add, every time we add, we check. Every time we add, we check. Right? Now, so every time we check, we also check previous. Now, this allows us to, wait, isn't this the same as this? Yeah, this is the same. Because we add, we find the next one, right? And then we just keep adding. I know that's the same idea. That's exactly the same idea. Not what we do. Well, not no. That's the same idea, which will time out. All right, no, this is not working. Heap. Multiplying a prime with previously generated upper number. All right, so I just read the idea. I didn't keep reading. So the new will be something times a new it is like to generate a 1 by 1, right? So if I have these already generated, what we're saying is the new value must be one of these multiplied by one of these. Huh. It must be one of these multiplied by one of these. That is true. That is true. Because that's what I was doing. I just had a new thing. Divided must appear in this. Okay. So it'll be one of these multiplied by one of these would generate the next value. But we want to generate the next value which is smallest value that's bigger than the current biggest. Right? So what? We just go 1 by 1. Multiply 1 by 1. That seems stupid. Right? That seems stupid. And then how? How do we get this? I say use heap. I mean, if you use heap, Nope, nope. Keep reading. Alright, so this is a common solution from ugly number 2. Find the next. Is OKN. So for everything in it, and everything in it, I say ugly I equals the minimum of this, and so we're looking for the minimum value. So everything in here multiplied by everything in here, and now we're looking for the minimum value. Hold on, I don't understand. And then next, we set to max for everything in the primes. We find the primes times ugly index j. What's index j? Index is a new integer array of primes.length. Ugly I, which is the next ugly value, right? So for each ugly value is going to be the minimum value, that's every prime multiplied by ugly index j. Ugly index j. What's ugly index j? J is for each prime numbers index, and ugly that, and a slip duplicate. I don't understand. I don't understand at all. New is generated by multiplying a prime with previously generated ugly number. No, this one's not helping because it has to be based on the other thing. I don't know the ugly number 2. K sorted list. 1 times, 2 times, 4 times, 7 times, and 8 times. Okay, so ugly number starts with 1. And I'll have this. And then it's 2. Okay, so wait, what does it mean? We have 2, 7, 13, and 19, right? And all the ugly numbers is going to be hold on, all the ugly number, it has to be the previous ugly number, multiply it to everything of this. That's true, that's true. We've done that already. So the first ugly number is 1, we know. Therefore, we're going to do 1 times this. Right, we're going to do 1 times this. Now, after we do 1 times this, we obtain new ugly number, which is 2, 7, 13, and 19. Right? Then the next round will be 2 multiplied by this. Right? And once this is done, then the smallest is 4. So we do this each time. We'll grab the smallest. Now we're not really grabbing the smallest. Like every time we grab a value, we need to throw it away. We grab a value, we throw it away. We pop. Oh, we pop. We grab the so yeah, okay, hold on. So we have a heap. Start with 1, and then we pop 1, right? So we pop 1, then we generate the next round of values, which is 2, 7, 13, 19, right? And then we pop 2 to generate the next round is 4, 14, 26, and 38, right? And then we pop again. Not just one, we pop, we get 4. And then we get another one. And next one we pop will be 7 because 7 is added to the heap. Now we pop. We keep adding and we keep popping, we keep adding. So we added 4. Every time we add 4, we pop 1. Add 4, we pop 1. So this list will keep growing. And at the end, we just need to count how many times we pop. But there will be duplicates. Now I see what it means by duplicates. Yes, there will be duplicates. But duplicate is fine. Just would pop out if it's a duplicate. If it's a duplicate, it'll be the same as the previous one, right? So we just keep check. If it's a duplicate, we just keep popping until a new one comes out. Oh, ooh, this is good. This is good. So we just import heap q, right? The heap solution from the discussion, but I have not read the code. So the idea is that each new ugly number must be produced by multiplying the ugly numbers already found, one of the ugly numbers found with one of the primes. Thus, we can create a heap for all the ugly numbers found. Right, we keep a heap for all the ugly numbers already found, and then we can pop the smallest. Right? We then pop the smallest of these ugly numbers, and pop the small and keep the count. The smallest ugly number is the count ugly number. And for each for each popped ugly number, we put in another round of ugly numbers by multiplying it with each primes. Therefore, here is what we're going to do. So we're going to say ugly equal to 1, right? And count is equal to, what is count? Count is 1 because we have ugly number already. And then what? Then we can say, okay, while count is smaller than n, how about count equals 0? So we can do the first one, count equal to n, and then current ugly will equal to heap q dot heap pop ugly, right? So current will pop out because it's smaller than. Actually, how should I do this? Count current, they're all 1. So if it's smaller than this, and if it's this, then we just return current. Now current will pop out. Then for p in primes, well, we can actually do current times p for p in primes. Then we do heap q dot heap push. Heap push. Wait, what's the signature of heap push? Heap q dot heap push. Param and item. So heap first. So heap push ugly. What do we push? Current times p. Right? So we push this into the heap, all of it into the heap. Right, current is this count plus equal 1. And now everything is pushed in, then come out, then we return. Okay. I don't know what 50 is, so I'm just gonna. Oh, I don't need to, right? I can just give actually. Let's just try this. Oh, there's no solution. Ooh, first one's not right. Heap pop. Push everything, we always pop the smallest. Right? Why would it come out 26? Because if we pop out the smallest. Hold on. Let's print the count and ugly out and see what happens. Right? Let's count 1, 2, 3, 4, 5, 6, 7. Oh, I forgot to handle the Jesus. Alright, so I need to remove the duplicates. Ooh. Okay. New current while while true, new current is equal to heap q dot heap pop ugly, right? Say if new current is equal to current, then continue, right? And we're gonna do again, if it's not equal to the current, then we say current equals new current and break. And the current, we can set it to 0. That's still not right. Put a 28. New current is gonna pop, so all the smaller pop out, right? And oh, I see. It might not be inside. Okay, we can do a set. So instead of count, because every time it pop out will be the smallest one pop out. Right, so every time pop out, it will be always the smallest pop out. It's just that every time we pop and the smallest gets popped out, and then will be multiple smallest. But if there's multiple smallest, why will this one not work? Hold on. Let me again print count and ugly. Okay, so 13 popped out, right? And then I have two 14s. Why did I count 14 twice? How did 19 come in? Wait, seriously? Oh, because I have 19. Yeah, I have 19. Well, how does 14 come up twice? So ugly is here, so 8 will pop out. And the previous one is 7. Okay. Now 14. Well, true, current, new shall be. No, this one's fine, 14 pop out. And this is the problem. Current is 14, right? If I count current is 14. Oh, I think this is right. It's just because 28 is right before 32. I just have to count one more. Because current is 0, right? And ugly is already 1. Can I do current at 1? Well, okay, so while ugly Yeah, we can say while ugly. And this will be this. This will be 1. Right? And I say wow ugly. Oh, there's nothing. Then this is still 28. Nah. 1 and 1. Current 1. Wow, ugly. So I'll just say count as 0. Yeah? How about count as 0? There we go. Count as 0. Current is 1. I'm gonna come in. Wow, ugly. That's actually fine. The base is wow, true. And then we say the new one. If the new one is the same, then I just keep going, keep popping until the new one is not the same. So I set current, the new one, come out. So now I have a current. Now a plus equal 1. And push everything in. Okay. Let's try this one. Basically, I'm going to run this. Huh. We're still in a timeout. What the heck? This is a log. Yeah, we do have to do this. Or do we only push in? Let's try it. Probably still timeout, but nope. Hey, what did I not do right? Mm-hmm. A priority queue. Okay, this is just put everything into the priority queue. Get this entry out. Prime 0. Number is entry 0. Prime is entry 1. Index is entry 2. Number not equal to numbers I minus 1. What's nums? Oh, nums. Nums I equals num. And offer again. Prime times, what's prime? Prime is this. Prime times nums index plus 1. Prime index plus 1. the value of the node. Prime means which sorted list this node is in. The index tells how far we have gone in that list. Merge list. So we have these lists, right? Now we need to know what is the, this is the start. And the times 2, okay? And we find which one to do. So we have the smallest of all of them. Nums index plus 1. I still don't understand. Okay, so what offer is num is the value of the node. Prime means which sorted list. Okay, prime. And index. Index, everything is 0. So index is on this, which index it is. Okay. And every iteration we just add one number. Every iteration we add one number, okay? So at index 0, we get all these 4 numbers. So that's what it means. And then num 0 is 1, that's true. And I equals 1 is the next index. So I smaller than n, yes. And so we pick the smallest one out. Among these, I pick the smallest one out. Okay. Now we have the number, which prime it is. And then we need to find the next one on this list because I'm merging these lists. I'm merging these lists, so I have the first one. So I need to find the smallest among these. So basically, I'm putting these in the priority queue. These in the priority queue. So every iteration, they will have different progressions, right? And then every iteration, we pop out the smallest among these. Okay, so pop out. Now we know which one belongs to, so I just progress it to the next one, and I'm pushing back in. Ah, this is bad. So this is wrong again. Wow, this one TLE again. Apparently, I did not fully comprehend the idea behind priority queue. All right, attempt number 3. All right, number 3. So this time I read the discussion post. And now I finally understand. This problem is the same as merging sorted linked list. Merging sorted list. Yeah, it's the same as merging sorted list. Each list is a multiple of each prime, and each factor to multiply is to multiply the primes are are all each factor belongs to the ugly numbers already found. Yes, that's the key. It's not times 1, right? You have all those factors. Because every number, if it is an ugly number, then I divided by it must appear previously. Therefore, if I have a list of ugly numbers, then the new ugly number must be produced from multiplying this to everything, right?